Hello everyone, and now we're going to be talking about Newton's method. I'm not going to do a derivation of this. I'm not going to explain this. This is actually it's in the PowerPoint slides and it's in your book. I am going to present to you a walkthrough of how you can use Excel to apply Newton's method very simply and get solutions this way. And we're going to do it again with the same expression that we've been using, this x cubed minus 17x plus 12. Why? Because, well, it's convenient. So let's start. In order to do the Newton's method, you have to have an old guess, you have to have a function of old, which is your function, and the derivative of your function. So we just need to have a new expression defining our derivative. The derivative of this expression is 3x squared minus 17 x, or not 17x, but just 17. There you go. So that's our derivative. So we can create our columns. In this case, we're going to say our x. We're going to say our f of x. And then we're going to say our f prime of x. So in this case here, I am going to say this is our x old, and I am going to put this as 0.8. This f of x is going to be what is it? It is our x cubed, which is x cubed minus 17 times x plus 12. Alright, and then we're going to have f prime of x, which is going to equal to 3 times x squared minus 17. Great. So we have this, we have this, we have this. I'm going to make this more convenient for us so that we can iterate on this. And I'm going to create a new column out here, which we'll just call x new. Okay? Now, x new, based on this, is going to equal to x old minus f of x divided by f prime of x. And we have a value here. Now, to iterate, we just have to say this becomes our new x old, and we can just copy and paste these down appropriately. And if all goes well, we can just copy and paste this down, and we get this lovely result where f of x is converging to 0, as it should. We have over here a value that's converged where x old and x new equals each other, and so we found a solution. Wonderful. Now the hope is when we enter in other values, we can get it to converge to other solutions. And lo and behold, when we enter in now x a negative 5, we are converging to the next nearest solution in this equation, which is negative 4.43. If you remember from the plot, we had another solution that was closer to the positive 5, so I'm going to put 5 in here, and lo and behold, we converge to 3.71. I don't seem to be like to say lo and behold. Maybe that will be the password for this video. But here you go. You have 5 comes down to 3.71, and I believe even if you take a pretty rotten guess of 1,000, you'll notice you're still not close to that, but it's well behaved enough that it should converge down to the right answer if we give it enough time, and sure enough, it does. So this is the advantage and the power of the Newton's method for solutions. Again, probably the biggest trick with it is it's only really useful when you can take a simple derivative of your expression. Most of the time, that is probably the case. It's not. It's very rare that you'll have an expression that you can't take the derivative to. It's just it can get very cumbersome and ugly in the process. So hence the reason why you normally would have this order of progression of simplicity to more complex as needed. So to summarize all of this taken together is with Newton's method, you're going to have to have a guess that can be converged to a spot. If you were in right numbers, you have to try to guess different numbers so you make sure you get all the possible roots of the system. And you have to note that sometimes in your approach, you need to be differentiable. It may not always be the case, and may be something that you need to consider. But to summarize all the techniques we've talked about, again, you'll have two methods searching for roots. Method one where you guess and check, and the other one where you're actually just looking at plots. Direct substitution, where you're using the form of the equation of f of x is equal to x, and very easy to tabulate and set up, and doing cell iteration, but may not always converge. And then Newton's method when it's possible. So I think that will end this discussion on iteration, and the next topic we'll talk about is optimization. So look forward to that video. Thank you. Bye.